So welcome back to chapter 2. We're going to move on to part 3 and talk about the chemical reactions in general and properties of water. So chemical reactions are anything when you make a chemical bond or break a chemical bond. In general, that's a chemical reaction. So anything on the starting side is going to be called the reactant, and anything on the finished side is going to be called the product. In this example, we see the reactants are on the left and the products on the right, and we know that these are reactants not just because it says reactants right there, but because the arrow is saying this is the way the chemical reaction is going. Arrows can go both ways, just so that you know. And we'll talk about that in a minute if the arrow is pointing in a different direction. But for now, the reactants are on the left and the products are on the right. One thing to notice is that the same number of reactants, atoms in the reactants, are also being found in the products. They've just been rearranged. So here we have 2 hydrogen gas molecules, and here we have 1 oxygen gas molecule. And when those encounter each other and give it a little energy, they can rearrange and form into 2 water molecules. Notice that the 2 oxygen atoms are now redistributed. Each one has 2 hydrogen, H2O. One of the things that's very interesting that we'll be looking at later in the semester is photosynthesis. And photosynthesis is a really important chemical reaction to life. Without it, life as we know wouldn't exist on this planet. In this case, sunlight is powering the conversion of carbon dioxide and water into glucose and oxygen. Now I have a little typo here. This should say products, and I'm sorry about that, but just pretend that it says products. Chemical bonds can be made and they can be broken, and those can happen within the same set of chemicals. You can have the reaction going forward, making the product, and those products can actually go the other way or be reversed and reform the original reactants. When this is happening at about the same rate, where it's going forward and reverse, we call that chemical equilibrium. Again, one of the most important concepts that we talk about is the hydrogen bond. And hydrogen bonding happens in water, which we did cover in one of the earlier videos. All organisms are made mostly of water. You are made mostly of water. And a lot of organisms actually live in an environment dominated by water. In a way, all the water trapped within your body is your body living in an environment of water. It's just trapped within your skin, inside of your body. Remember that water molecules are polar, and that means that oxygen has that partial negative and hydrogen has that partial positive charge. And 2 water molecules are held together by hydrogen bonds. This is a bit of review, but that's okay. It's so important that we're just going to cover it again. At any moment, water molecules are hydrogen bonded to their neighbors. So remember that those dots indicate a hydrogen bond, and the highly electronegative oxygen is attracted to this less electronegative. We say it has a partial positive region of the hydrogen atom within the neighboring water molecule. This is such an important concept to get. Hydrogen bonds are between different molecules. So the negative region of this molecule is attracted to the positive region of this molecule. And that's true all over this water molecule. We have those attractions, those hydrogen bonds happening in each of those water molecules. Because water is attracted to other water molecules in hydrogen bonding, this gives water 4 very important emergent properties. We used that word before when we were talking about sodium chloride, right? Sodium is a solid, chlorine was a gas. And when you combine them, you came up with this ionic bond that is sodium chloride, which is something very healthy for you in small amounts. Remember, don't go crazy with it. So there are 4 emergent properties of water. Cohesive behavior, which we call cohesion. The ability to moderate temperature. That means like water, it takes a long time to heat water up and cool it back down again. Water molecules expand when they freeze, and it makes it very versatile as a solvent. We'll go through those one at a time. So cohesion. What's cohesion? Water molecules linked by lots of hydrogen bonds stay close together. That's what cohesion is. It's very straightforward. They stay close together. Cohesion. Cohesion, due to hydrogen bonding, does this other thing though. And what it does is it causes water to be able to be transported very easily against gravity. What that means is that water can flow up a narrow tube like in plants. And that's called adhesion. Cohesion was when hydrogen bonding between water molecules caused them to stick together. Adhesion is when water clings to another surface, like that of a plant. So here we go with seeing the adhesion in plants. And again, cohesion is definitely going to be playing a role. Cohesion between water molecules is going to allow that water to be conducted up through the plant through adhesion. Another thing that's interesting about cohesion is that you get something called surface tension. And surface tension is basically what happens when you see insects walking across the surface of water. It's actually really hard to break the surface of water. And this is due to cohesion. Surface tension is related to cohesion in a very useful manner. I talked to you about how some organisms can walk across water. This is a spider walking across water, and its little depressions here are not because of something special about the spider, it's because of the properties of water. Another thing that we talked about was that water has the ability to be moderate. So water does absorb heat from air, and it releases stored heat into cooler air, and water can actually absorb and release a lot of heat into the air without the water changing its temperature. Water is very slow to change its temperature, and that's important for life, and it's important for the way the earth works. And so we definitely need to learn about what happens there with water and heat. So a couple things here. We're going to get into the idea of heat for a while so that we can talk about the importance of this in water. And when we talk about heat, we have to talk about energy. And there's definitely different kinds of energy. There's kinetic energy. That's the energy of motion. We'll definitely be talking about that later in the semester. There's also thermal energy, and this is the measurement of how much kinetic energy there is due to molecules moving. So thermal energy really is about the motion of molecules. In general, we measure the motion of molecules with temperature. And so temperature is reflecting the average kinetic energy of molecules. It's all about motion though, isn't it? Kinetic energy is motion. Think about waving your hands. That's kinetic energy. Thermal energy is just thinking about molecules moving. So thermal energy is able to be transferred from one bit of matter to another bit of matter. Anytime you can transfer energy from one bit of matter to another bit of matter, you call that heat. So heat is not the same thing as temperature, but they are related because heat is something where you transfer that energy. And we measure heat in calories. So a calorie is the amount of heat is required to raise a temperature of 1 gram of water by 1 degree C. When you think about calories in food, it's actually not calories, they're actually kilocalories. A kilocalorie is where you raise the temperature of water. It's basically 1,000 times that. So 1,000 calories is 1 kilocalorie. Another way of measuring heat is the joule, and this is the conversion for joules. And I'm not going to make you do any conversions of joules and calories. I just want you to know that that's a measure of heat that we're going to be mentioning every once in a while. It's a measure of heat. Water has a really high specific heat, and specific heat is just the way to say that you have a certain amount of heat that has to be absorbed, or you could talk about the amount of heat that has to be lost for 1 gram of whatever substance you're talking about to change its temperature by 1 degree C. So remember, we just defined water as 1 calorie per 1 gram. That's what heat is for water. And everything else has a different specific heat. Think about some metals that can heat up really quickly. That's got a much lower specific heat. It takes less energy. Water has a high specific heat. And it's high because of the hydrogen bonding. When you are heating up water, what you're doing is you're breaking hydrogen bonds. And when heat is released from water, you're actually forming hydrogen bonds. So because those bonds are forming and breaking, that's why it has a high specific heat. And that's why it's so hard to take so long to heat up water. Keeps the fluctuations of temperature really low. A really practical application of this is thinking about the ocean. So here's the Pacific Ocean, and in this region of the Pacific Ocean, it's 68 degree water temperature. And right along the edge of that water, you have a couple of major cities. There's San Diego and Los Angeles. There's Santa Barbara, which is a smaller city, but still, it's a pretty cool city. All of those cities have average temperatures in the 70s. San Diego's average temperature is 72 degrees. Los Angeles is 75. Santa Barbara is 73. It's all because of the specific heat of the Pacific Ocean. As you move inland, not even very far, just a little bit. Oops. Sorry about that. Don't you love it when you get interrupted by a phone call in the middle of making a video? Okay, so we were talking about specific heat of water. As you get farther and farther away from the ocean, the less you're affected by that specific heat. And so it gets hotter and hotter and hotter until you get into the desert of Palm Springs and San Bernardino. One of the things associated with having a high specific heat in water is having something called evaporative cooling. So evaporation, vaporization, same thing, is when you go from liquid to gas. And there's a certain amount of heat that it takes to go into the vapor state. And the heat of vaporization is the amount of heat any liquid requires for a gram of that liquid to be converted into a gas. As liquid evaporates, it cools because that the heat is actually being taken away, and the cooler region is left. So evaporative cooling of water helps stabilize temperatures in your bodies of water as well as in living things. We talked about how water, when it cools, becomes ice, and that is a very crystalline structure. We'll see that in a second. But one of the very interesting things about cold water, as opposed to anything else that freezes, is that solid water, ice, will float in liquid water because the hydrogen bonds in the ice are more ordered, they're more crystalline, and that makes the water less dense when it's frozen. Water can reach its greatest density at 4 degrees C, and that's very close to freezing. So if ice sank, all the water would eventually freeze, but because ice floats, it actually acts as a bit of an insulator, and you can see here that life can actually thrive below the surface of the ice, like this little shrimpy guy here. And it floats because of this very, very crystalline structure, making it less dense. When it's liquid, the hydrogen bonds are actually closer together. So floating ice can insulate the water, as I just said, and allow life to live underneath that frozen surface. Unfortunately, due to global warming, we're have less and less frozen ice, and that actually puts a whole bunch of biomes in danger. And here you can see some of the organisms that are in danger because of the reduction in the here is the ice sheet at the North Pole. And you can see that that's reduced significantly in just a very short amount of time. This is just 30 years. Now in 2020 and beyond, that ice sheet is shrinking, is just much, much faster. And this has put things like polar bears and black guillemots and walruses at risk of going endangered. Also whales and certain fish species that rely on like these little planktons. So it really does change the entire ecosystem of the Arctic regions. The last thing that we talked about as an emergent property is that water acts as a solvent. And so let's talk about some terms here, some basic terms. Water is a solvent. A solution is any liquid that's just homogeneous, is just equally mixed through. That's what a solution is. You can have solution that is water and salt, right? Saltwater solution. It's evenly mixed between water and the parts of the salt, sodium and chlorine. A solvent is the thing that's doing the dissolving, and a solute is the thing that's being dissolved. So in the example that I just gave you with sodium chloride, and I'll show you this on the next slide too, the solvent is water, the solute is the salt, and when it's all evenly mixed, it's a solution. If it's in water, like the example I just gave you, we say that's an aqueous solution. Aqueous referring to aqua, right? That refers to water. So here's that example, sodium and chlorine and all of this water. As you put salt in water, it slowly starts to dissolve and moves into equally being distributed throughout that water. The reason this works so well is because water's got that partial positive and partial negative. And so the partial negative of the oxygen in water is attracted to that positive sodium, and the partial positive of the hydrogens in water are attracted to that negative ion that's chlorine. So when an ionic compound is put in water, each ion is surrounded by a sphere of water, and we call that a hydration shell. So this is the hydration shell around chlorine, and this is the hydration shell around sodium. Water can dissolve lots of things. It doesn't have to be an ionic bond in order for water to dissolve it. As long as the water is trying to dissolve polar molecules. So large polar molecules, we'll learn that protein is a large polar molecule. Proteins can dissolve in water if they have some ionic or polar regions to them. Like you see right here, this is one protein molecule and it's surrounded by that shell of water. So we're just going to keep moving on here. We don't have that many slides left to go. The next big term that we need to learn about is hydrophilic and hydrophobic. Hydrophilic literally means water loving. It has an affinity for water. Hydro meaning water, philic meaning to love or to like a lot. Hydrophobic means afraid of water. Literally, phobia is fear. It's not like the thing is afraid of water. It just doesn't have an affinity to water. It's not attracted to the polar nature of water. So oil is hydrophobic because they're relatively nonpolar. They're almost completely nonpolar. Remember that nonpolar means they don't have a charge. So only things with charges are going to be attracted to water. Oil is hydrophobic because it doesn't have a charge. And that's going to come up, be important in the next coming chapters. Most chemical reactions do involve the solutes being dissolved in water. And there's, depending on how much solutes there are or the number of molecules that are in there, that's how we talk about the word concentration. So how many solutes are in an aqueous solution is what we say is the concentration of that solution. And so we're not going to learn this math here. I just wanted to show you that you can easily calculate solutions. In this class, we just really think about solutions as percentages almost, but you can calculate it using molecular mass, and you can figure out the moles and the molarity. Just when you hear those words like molarity, just think about how many solutes there are in water. The bigger the number, the more solutes there are. The reason that I bring that up at all is because this is important for thinking about this concept of acids and bases, and I really wanted you to have the term concentration. So when you have water, sometimes you can separate the molecule of water into ions, like literally ions. Instead of being H2O, you have H and OH. You've got a hydrogen ion, and you have an hydroxide ion. So this is our hydrogen ion. It's just H plus. That plus meaning it's given away its electrons, and it's given its electron over to the hydroxide ion. Another name for a hydrogen ion that we use a lot in this class is the word proton. Remember that a proton is just one single positively charged subatomic particle. And if a proton is not matched up with its matching electron, then it's a bare proton. So sometimes those bare protons will join up with water to make something called hydronium, or H3O. And because it's got an extra hydrogen ion, it is in fact an ion itself, and that's what that little plus there is for. So conventionally speaking, when we talk about hydronium ions, we actually just use the proton. That we just use that symbol right there, H plus. So just kind of be aware of that as we go along. Just showing you really quickly what two water molecules happens to them in water. One of them can flip over to become a hydronium ion, and the other becomes a hydroxide ion. But again, remember, we tend to symbolize this as simply H plus, just to simplify things for us. Water can dissociate. It happens. It's not super common, but it's important. And it's also reversible. Remember, reversible means that the arrows go both ways. And here's the first time that I'm pointing out where a chemical reaction has the arrows going both ways. So remember we said that was reversible. So the proton, the hydronium ion, the hydrogen ion, the proton, and the hydroxyl ion are very reactive, and when they combine, they form water. Solutes, called acids and bases, can disrupt that balance of those two together. Acids will increase those proton concentration, and bases reduce that free proton concentration in the water. So it could look a little bit something like this. If you've got a strong acid like hydrochloric acid, that's HCl right there, and you put the H and the Cl in water, what you get is, oh, look at that, that's that proton. And remember that proton, whenever you increase protons in water, right, you've got an acid. So this right here, the thing I'm circling right here, this proton, that's why hydrochloric acid is an acid, because it's increasing the number of protons in the water. Now ammonia, which is NH3, can act as a base. It can attract a hydrogen ion out of that water. So when it attracts a hydrogen ion out of that water, it's now a base. This is very reversible. Here we go as this reversible action. So it goes backwards and forwards between those two forms. So again, we have this, oops, I'm sorry, I'm going the wrong direction. Sorry about that. Sodium hydroxide, on the other hand, is a really strong base. Let's take a look at it. Remember, we're looking at these hydroxide ions. Sodium hydroxide can dissociate, and you get these hydroxide ions. And if you have these hydroxide ions, they combine with the protons to form water. So if you have these hydroxide ions, they're going to pull out those protons out of that water, and that's what makes it a base, the presence of those hydroxide ions. If you got an equal number of protons and hydroxides, you have a neutral solution. There are sometimes you have weak acids and bases, and here's an example of weak acid. This is carbonic acid, H2CO3. It's releasing a proton there, but that it's considered to be a weak acid because it doesn't let go of those very often. Here's where we're going to talk a little bit about pH. Again, I'm not going to make you do any of this math. I just kind of want to familiarize you with it. So if we're looking at an aqueous solution, we call that, and then we're looking at the balance of protons and hydroxide ions, we call that pH. And pH, the H in pH is the hydrogens. So a pH, and the P is kind of like percentage. It's an algorithm. You got your superscripts here. You take the logs and everything. But honestly, we're just looking at concentration. pH is talking about the concentration of protons. In a neutral aqueous solution, your pH is 7. In a very acidic solution, you're going to have a low pH, like battery acid and lemons and vinegar, and things that have a very high pH, you're going to have things like bleach and oven cleaner and sodium hydroxide, ammonia. Those are going to be up here. Turns out that most biological stuff are right around the 7 mark, with a few exceptions that we'll talk about, like gastric juices. That's what happens in your stomach. Most of the stuff in our bodies have the pH right around 7. Our body does really like it to be around 7, so our body produces things called buffers, and this just stabilizes the concentration of the protons and the hydroxide ions. So buffers are important. Most buffers are weak acids, and they can balance everything out. Carbonic acid is a common buffer in human blood, and so it's going to donate its proton, which drops the pH, and now it becomes a base and can accept a hydrogen ion, right? It goes backwards and forwards. So a nice little buffer for the blood, keeping it at a nice pH of about 7. Acidification is really a a tragic thing that's happening in our oceans right now. We have a lot of carbon dioxide as a byproduct of burning oil and gas and coal, those fossil fuels. And when that carbon dioxide dissolves in seawater, that forms carbonic acid. And that's what's causing the ocean to be acidified. We have increased the amount of carbon dioxide being absorbed by our oceans by 25%. And what I mean by that is that of all of the carbon dioxide that we are forming by burning fossil fuels, a lot of that's absorbed into, about 25% is absorbed into the oceans. So let's just take a real quick look at what happens. We're burning fossil fuel, for example, by planes, trains, automobiles, all those reasons that we burn fossil fuels. That carbon dioxide byproduct gets put into the oceans, and that gets turned into our carbonic acid. Goes through being bicarbonate first, and then all those protons get shuttled back and forth. Eventually, those protons get added to calcium, and that calcium gets broken down, and the calcium is really important for coral reefs. So one of the bad side effects of carbon dioxide is that it keeps getting passed along, and it breaks down coral reefs. This is really bad. We're predicting that the carbonate ion concentrations is going to decline by 40% by the year 2100. So in about 80 years. It's a huge problem. Coral reefs are something that stabilizes our ecosystems, and we are dependent upon coral reefs to help keep hurricane strengths down and preserve our land, the places that we live. All right, well, thank you for listening to my lecture on chemistry. I hope you learned a lot from it, and I'll see you in chapter 3.